It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. When we talk about artificial intelligence, it's tempting to picture an invisible, weightless brain floating somewhere in the cloud. But the truth is much heavier. Run a complex prompt, and you're actually spinning up thousands of physical processors inside massive, brutalist server warehouses, pulling raw electricity directly from the grid. We've moved past the phase where AI progress was strictly about writing clever software. We are currently living through the most aggressive physical infrastructure boom of the 21st century. The raw currency of this boom is compute, the actual hardware required to process and output data. Right now, the world's biggest tech companies are locked in a quiet race to secure exclusive access to these physical components for the next decade. Having the best algorithm isn't enough anymore. The future capabilities of these models are entirely dictated by who owns the physical hardware stack. To understand the scale of this scramble, look at Amazon. They are reportedly locking in a supply of 1 million NVIDIA GPUs by 2027. That is an astonishing consolidation of physical computing power. Because NVIDIA essentially holds a monopoly on these chips, billions of dollars in venture capital are flowing into challenger companies trying to build alternatives. Startups like Etched, backed by major players like Peter Thiel, recently raised $500 million at a $5 billion valuation just to compete in this hardware race. But the nature of the race is changing. For years, the focus was on training, using massive, brute force computing to teach an AI model how to think over several months. Now, the battlefield has shifted to inference. Inference is the phase where the fully trained model actually runs in real time, responding to your prompts and executing tasks. Running inference efficiently requires specialized hardware that prioritizes speed over raw power. That's why Microsoft rolled out its own custom 3nm inference chip, the Maya 200, and why Amazon Web Services partnered with Cerebras to build high-speed inference directly into their servers. This diagram shows the structural difference. On the left, you have training clusters, massive, power-hungry blocks designed to process mountains of data. On the right, inference architecture relies on streamlined, fast-flowing data pathways built to deliver answers in milliseconds. You could build the most sophisticated AI model on the planet, but without highly specialized inference hardware to run it cheaply and instantly, you can't actually deploy it to millions of users. Even if you buy millions of processors, you hit the next physical limit, wiring them together. When you have tens of thousands of chips trying to share data simultaneously, the signals crash into a literal bottleneck and overload the system. Standard copper networking cables simply cannot move information fast enough. As a result, expensive processors sit completely idle, waiting for data to arrive. At this scale, even a microsecond of delay cascades into a total system collapse. To bypass this traffic jam, the industry is abandoning traditional wiring and pivoting to optical networks. They are using lasers to transmit data between chips at the speed of light. This chart shows Broadcom's recent industry projections. They anticipate that demand for custom AI accelerators and the specific networking components required to connect them will exceed $100 billion in sales by 2027. Notice the specific slice dedicated to connectivity. NVIDIA recently invested $2 billion directly into Lumentum, a manufacturer of optical components, to guarantee a steady supply of these lasers for their own server racks. The processors get all the headline attention, but the fiber optic cables connecting them dictate how fast next-generation AI can actually operate. AI is moving fast, science is moving fast, technology is moving fast, and most updates online are either too complicated or just pure hype. Welcome to Future Explained, the channel where we take the latest updates in AI, technology, and science and explain them simply. But lasers and processors both share one uncompromising requirement: massive amounts of electricity. Meta's Mark Zuckerberg recently laid out plans to build tens of gigawatts of new data center capacity over the course of this decade. To put that in perspective, a single gigawatt is enough to power a medium-sized city. Drawing that much juice puts immediate strain on the physical world. In the US, the White House and state governors are actually pressuring PJM Interconnection, the organization managing the power grid for over 60 million people, to run special energy auctions. The goal is to allow major tech firms to bid on building new power generation facilities. specifically to prevent local consumer electricity bills from spiking as these huge data centers come online. This energy and hardware crunch is attracting heavy industrial capital. Jeff Bezos is reportedly exploring a $100 billion fund strictly to acquire and modernize physical manufacturing firms using AI. The pace of artificial intelligence is no longer dictated by the math inside the code. It is gated by the physical limits of our national energy grids. When a technology requires gigawatt-scale power and millions of physical processors to function, it stops being a standard corporate software product. It becomes critical national infrastructure. Governments are recognizing this and stepping in to build their own sovereign hardware. The UK, for example, is massively expanding its Cambridge AI research resource, installing a new system called Dawn to give local researchers free access to top-tier supercomputing. With that scale comes a need for rigorous verification. The UK also launched a £10.5 million Centre for AI Measurement to test and evaluate the safety and reliability of these highly capable models before they hit the public. Economic stability and national security now require a country to own both the physical computing stack and the testing frameworks to keep it in check. All of these massive background efforts, the server farms, the laser networks, the grid expansions, are finally materializing on the devices sitting on your desk. Because companies have cracked the code on high-speed inference, they can deploy highly optimized, lightning-fast models. OpenAI's recent release of GPT 5.4 Mini and Nano is a direct result of this, built specifically for high-volume, low-cost tasks. Pair those optimized models with specialized agentic processors like NVIDIA's new Vera CPU, and you get a massive leap in capability. We are moving from passive chatbots that wait for your text to active desktop agents that control local files and execute workflows autonomously. Every time your desktop agent seamlessly writes a block of code or organizes a spreadsheet, it is riding on the back of sprawling power grids, custom optical interconnects, and billions of dollars in specialized inference chips. The story of AI right now is the successful deployment of a physical, industrial machine. The old debate separating software from hardware is completely obsolete. The trillion-dollar infrastructure build-out is no longer theoretical. It is a certified reality. Future Explained brings you the latest AI, technology, and science updates, explained simply. In every episode, what happened, why it matters, and a real example, no hype. Subscribe for shorts plus deep explanations. So if you want to stay up to date with the future without getting lost in hype, subscribe to Future Explained and comment below, what should I explain first, AI, technology, or science?